Okay, I'm not sure if my share screen is working. Let me share my screen again. Okay, so oh yeah. Thank you very much for pointing that out. So brings our today's topic, heat transfer. Basically, it is a physical discipline of thermal engineering that concerns the generation, the use, conversion, and most importantly, the exchange of thermal energy or heat between different physical systems. There are basically three mechanisms. Number one, known as the conduction. It describes the heat transfer via direct molecular collision. And the second is the convection. It is the heat transfer via the movement of fluid. And lastly is the radiation, which is the heat transfer, which doesn't require any medium, but only the emission of electromagnetic wave. All right, so take a look at the first one, the conduction. It describes the transfer of thermal energy, which is always from the hotter medium to the cooler medium. And that is to say, there is always a temperature difference which causes heat transfer. And in this process, there are a few important variables. First going the most important one, the temperature, and then is the amount of energy transferred. I write as E in the unit of joules, followed by two heat coefficients. First one being the heat flow or heat transfer rate, Q. The unit is joules per second, or you can also write it as watts. And lastly is the heat flux, which is the heat transfer rate divided by the area. And it has a unit of watts per meter square. All right, so on a microscopic level, the heat conduction is basically the vibration and collisions of molecules. And the extent of their collision is different. That means from the hotter end to the cooler end, there's always kinetic energy transfer. And in a macroscopic scale is the heat conduction. So that is to say, it kind of reminds me of the human wave sometimes the football fans do in the stadium, that is always passed from one active side to the side which is less active, and in the end it goes in a cycle. Okay, here comes the first equation of the day, which is known as the Fourier's law of heat conduction. It defines the heat transfer rate, Q equals to minus K times A times dt over dx. It means it is proportional to the thermal conductivity as well as the area of thermal conduction, and is also proportional to the ratio of the difference in temperature divided by the distance between the two surfaces. And here is also, you can define the heat flux, Q double prime. Basically, it equals to Q divided by A. And this kind of equation is known as the ordinary differential equation. It is quite easy to solve because there is no variable. Everything is known, so you can easily calculate these values. All right, I just mentioned a definition known as the thermal conductivity, and it means it is the ability to transfer an object's ability to transfer the heat via conduction. In gas, it is through the process of collision of randomly moving molecules. In liquid, it is collision of more closely spaced molecules as well as the molecular forces. And importantly, in solids, it is delivered by the lattice vibration as well as the transport of free electron. That is to say, a good electrical conductor is always a good thermal conductor. But think about this. Does it apply in the other way? Is a good thermal conductor always a good electrical conductor? The answer is no, because you can easily find examples as diamond, which doesn't conduct electric energy, but is a very good thermal conductor. There is also a thermal paste built based on silicone, also a good thermal conductor, but it doesn't conduct electricity. All right, I'm not sure if the equation reminds you of anything, so probably you have all heard about or learned about Ohm's law, and in which the current is defined as the difference of voltage divided by resistance. And in this model, the heat transfer rate has the same form. So if you combine a few items together, and the overall heat transfer rate is just the temperature difference at two sides of this object divided by the overall thermal resistance. So I assume that something very important is missing in the picture. What is it? Time. Time is missing in this picture, which means sometimes we have to deal with unsteady heat conduction. So I'd like to present this model describing the unsteady state 1D heat conduction. That is to say, the energy balance of this system is now divided into 4 parts. On the left-hand side of the equation mark, we have the energy conducted in the left phase plus the heat generated within the element. And on the right-hand side of the equation mark, we have the change in the internal energy as well as the energy conducted out of the right surface. So if you write it, it can be a long and tedious equation, but you notice something can be eliminated quite conveniently, and we can write it like this. So this equation is known as the unsteady state 1D heat conduction equation, and you can also shrink it into a heat equation by dividing everything with the thermal conductivity. Now that you have another derived physical definition known as the thermal diffusivity. The unit is meters squared per second. It describes the thermal conductivity subject to the density and specific heat capacity of this material. Okay, so what you see here is known as a second-order partial differential equation, or PDE. This is something that is not quite easy to solve, especially when it comes into the 3D space. How do you calculate the heat conduction through a cowl? Okay, quite complicated, but we have heard that nothing is particularly hard if you divide it into small drops according to Henry Ford. So this is something we can address using computer software. Anyway, if we conduct the heat conduction with laser absorption, we have to make some assumptions. For example, the laser beam we assume is uniform, and we assume the substrate is also uniform and planar. We assume the beam diameter is much larger than the thermal diffusion distance, and we assume the beam energy is absorbed at the surface only. So that we induce the absorbed laser intensity, that is the incoming laser intensity I0 times the A, which is the absorptivity of the material itself. And you can see the temperature is only subject to the product of these two times the material constant. And knowing which, we can do some basic calculation. For example, if we have a piece of aluminum, everything is known, and we have A0 equals to 0.26 gigawatt per centimeter square, we can work out that the temperature rise is 29.2 times 1000 Kelvin when the pulse ends, quite high temperature. Whereas we can also calculate the heat penetration depth, and according to the thermal diffusivity and the emission time, we know the heat penetration depth is merely 2 micron. But this is already so much deeper than the optical penetration depth, less than 100 micron, because we know aluminum is normally considered as an opaque material. It doesn't transmit light. And also, our laser spot size is something only between 10 micron to 10 mm, which means the heating can be quite localized, and this is the base of micromachining. Okay, so now you have learned 3 heat transfer mechanisms, and can you identify which was the one you used to keep comfortable? Okay, so I'll just nominate someone. So Xiying, you have been to UK, and was it cold, and what did you do?
Yeah, I've been in the I've been to UK myself, so what I do to keep myself warm, right? Very warm clothes and also social heat. Yeah, because usually there's always heat at school.
Right. So wearing more, which one do you think is the mechanisms you employed? It is actually convection, because essentially you have a lot of air trapped in the porous structure of whatever wear. And air is, number one, is a very bad heat conductor, and it will help to keep you warm. And number two, it also have to do with convection, because the air trapped inside kind of stop the wind from blowing on your skin. So basically, I'd like to say it's a combination of convection and conduction. Okay?
Okay, thank you.
Yeah, and staying indoors with the radiator on, I suppose, because I remember UK has that as well. That is basically radiation. Agree?
Yeah.
Okay,
Yeah.
cool. Yeah. And then for those who are staying in Singapore, I see Kenshawn goes to shopping malls. So could you explain which mechanism did you employ? The shopping mall is, sorry again, conduction? Yeah. Right. Right. Staying in cold air does you that, but what matters now is the air keeps flowing, and the flowing air takes the heat away more efficiently, which means you are basically combining both convection and conduction. But in this case, mostly it is driven by convection.
Yes, forced convection.
Right. So I think going to shopping malls also distract you from the temperature change by looking at different merchandise. I think that has something to do with what we say a calm mind or a set of mind also help us to cool. I think there's an old saying about something you cool yourself by not doing anything and not thinking anything. Anyway, it's not physics, it's just me joking around. Anyway, okay, let us wrap it up. So basically, let's do a qualitative quiz. Say if I am to laser heat a workpiece to go for the Guinness World Records, the highest temperature ever created in the lab. So how do I tune my laser and how do I choose my material? So material absorptivity, do I choose high one or low one? I think I'd choose high absorptivity, and then I choose something with low thermal conductivity because the heat will basically be trapped in there. And diffusivity also related to the conductivity. I also choose something with low thermal diffusivity. And in the meantime, if I have this laser, I would like to turn it to 110% of its maximum, and I'd like to keep the laser on time as long as I can. All right, so I think we have covered the following contents today. We have discussed the heat transfer's definition and 3 mechanisms. And we have introduced the microscopic mechanism of conduction, which is the molecular collisions. We've gone through the Fourier's law of heat conduction. We have compared steady and unsteady conditions, and then introduced very quickly a one-dimensional laser heating model. And we realized that is something localized, instantaneous, and intense heating, which is quite a powerful tool for our material processing applications. Okay, with that being said, thank you very much for attending this lecture. Thank you.